This is a lecture on what's meant by analog and digital. So first we're going to start with analog, and a word that's often used with analog signals is the word continuous. Okay, that analog signals are continuous in time, and a word that's often used with digital signals is the word discrete. That you have discrete values in time with digital signals. Now, a definition of analog that I like, and there's various definitions, but this is the one that I particularly like, and it's that an analog signal you can obtain, or the number of values that you can obtain from an analog signal is only limited by your precision level. Okay, and I'll give an example of what's meant by this. And what I have drawn here are two types of analog signals. This is an analog AC signal, okay, so a sinusoid that's continuous in time. And here's a DC analog signal that's also continuous in time, where this DC signal can vary between -5 and +5. So if it's a voltage signal, this would be -5 to +5 volts, and same thing here if this is a voltage sinusoid. Okay? So both of these signals, one AC, one DC, are both analog signals. Now, what this definition means is that if my precision level, you know, let's say I'm in a lab and I have a voltmeter that will only display whole volts. So if my precision level is whole volts, okay, I don't have decimal places or decimal place, well, then the number of values that I could obtain from either one of these analog signals would be all whole volt amounts. So 5 volts, 3 volts, 2 volts, 1 volt, 0 volts, and I could have -1, -2, -3, -4, -5. So with this precision level whole volts, I could obtain 11 different values from either one of these analog signals. But if my precision level was better, say 1/10 of a volt, okay, or tenths of volts, well, now the number of values that I could have from both of these analog signals would be much more, because I could have 5.0, 4.9, 4.8, all the way down to -5.0. So clearly, with better precision, I have an increased number in the number of values that I could obtain from either one of these analog signals. And if my precision level was even better, hundreds of volts, well, I could have 5.00, 4.99, 4.98, all the way again to -5.00. So clearly, the better my precision, the more number of values that I can obtain from an analog signal. Well, compare that with the digital case, because as we said before, digital, you have discrete values in time. Okay, so specific values, and you can't have any other values than those specific values. And the most common type of digital signal is a binary digital signal. Okay, this is the type of digital signal used in computers, where you can only have two values. Okay, so two discrete values in a digital binary signal. So here's some examples of digital signals. Here's a digital signal where the two possible values are +12 volts and -12 volts. And here's a digital signal where the two possible values are 3.3 volts and 0 volts. Now, in digital circuits and with digital signals, instead of using voltage levels, we often will use zeros and ones. And typically, if you have a binary signal like this where one value is plus and the other is minus, the plus value is called a 1, okay, and the minus value is called a 0. So these zeros and ones are just shorthand for the voltage levels. In an actual circuit, you're going to measure whatever the voltage level is, but we just use zeros and ones as a convenience. And typically if you have this type of digital signal where you have a plus value and a zero value, well, the plus value is the 1 and the zero value is the 0. Now, you may be wondering, well, how do you obtain precision with digital signals? You know, precision requires that you can represent many values with your various signals. And it would seem like that wouldn't be possible with a digital signal since there's only two possible values, a 0 and a 1. But you see, the way that high precision is obtained in digital circuits with digital signals is through coding. Okay, and what coding is just using multiple digital signals to represent something. Okay, where that something can be anything the designer wishes to represent with those digital signals. So, what I'm talking about here is that if you have one digital signal, okay, so one digital signal, which by the way, a digital signal is called a bit. Okay, so you see either one signal like this, or one signal like this, or one signal of any type of signal that just has two possible values. Well, that's all you could obtain from that one digital signal, is either a value of 0 or a value of 1. Okay, but now if I have two digital signals, okay, so 2 bits, well, with 2 bits I could represent more than just two values, because both those bits, both those signals could be 0 at the same time, or one of the bits could be 0, say this one, and the other bit 1, or this bit could be 1 and this bit could be 0 at the same time, or both bits, both digital signals could be 1 at the same time. So with 2 bits I actually could represent 4 values, okay? Where again, 1 bit I could only have a 0 or 1, so that's 2 values. Okay, well, if I have 3 bits, okay, 3 digital signals, I could come up with these unique values. I could have all zeros for my bits, or I could have this combination, or this combination, or this combination, or this one, and squeeze in the last one here. See, I could have 8 unique combinations of bits, so 8 unique values. Okay, so you see a pattern here. 1 bit I can represent 2 values, 2 bits I can represent 4 values, 3 bits I can represent 8 values. If I have 4 bits, that would correspond to 16 values, 5 bits, 32, 6 bits, 64, and so on. Every time I add a bit, I double the number of values that I can represent with those bits. So in theory, if I have an infinite number of bits, I have an infinite number of values, so therefore I could have an infinite level of precision. Okay, so that's how high precision is obtained in computer circuits, is through the use of coding. And there are various codes that are used in digital circuits. The most popular is the binary code, where we're using the bits to represent numerical quantity. Another popular code that's talked about in your book is the Ascii 2 code, where there you're using 7 bits to represent alphanumerical characters. So the characters you would find on a computer keyboard is represented by this code. And really what you can represent with these bits in circuits is anything the designer desires, okay? Because in of themselves, the bits are just voltage levels, right? These zeros and ones are just corresponding to various voltage levels, as we talked about. And what those voltage levels and those bits represent is determined by the designer of the digital circuit. So in the next couple of videos, we'll show how we can convert between analog and digital signals.